Hello friends, welcome to this lecture on Metamorphism and Ore Genesis by Dr. D.B.Guha. Dr. D.B.Guha did his MSc from Banaras Hindu University in 1979 and did his PhD from Punjab University in 1985. Dr. Guha served the Geological Survey of India from 1984 to 2017 and retired as the Deputy Director General of the Geological Survey. Dr. Guha has extensively worked in the metamorphic terranes of Rajasthan, and today he will be teaching us the metamorphic ore deposits and metamorphosed ore deposits. He will explain the difference between metamorphic ore deposits and metamorphosed ore deposits. He will also be highlighting the importance of field observations that can lead to mineral discoveries. He will be touching upon the discovery of the Bhukia gold deposit in Rajasthan, which is discovered essentially by relying on field mapping expertise and observing the detailed and anomalous behaviors in the field. Welcome, Dr. Guha.
I am Dr. D.B.Guha, ex-Deputy Director General of Geological Survey of India. I am going to speak on a topic metamorphism and ore genesis, which will be of interest to many people because most of the ore deposit in the tectonic terrain or the fold belts are metamorphosed or metamorphic in origin. Metamorphism is defined as the mineralogical, chemical, and structural adjustment in solid rocks to physical and chemical changes which have been imposed into it due to changing pressure and temperature conditions, or both. So, metamorphism will obviously change the mineralogical setup and the chemical setup and the structural setup of the individual minerals and the paragenetic minerals because of the change in the temperature and pressure. The process of metamorphism will change the structural grains of the rock. So obviously this process of metamorphism will change the pre-existing texture of the rock and pre-existing mineralogy of the rocks also. So new set of minerals will form, and obviously the mineral deposit will be a new one. The agencies which are responsible for transformation of these, which help in transforming the deposits due to metamorphism, are the activity of water and activity of carbon dioxide. Normally, this metamorphism does not form metallic ore deposits because ore forming minerals are rarely suffer mineral combinations, unlike the rock forming minerals which change due to the PT condition change in a paragenetic sequence. Like one paragenesis changes to other paragenesis because of reactions between two individual minerals or three individual minerals. So metamorphism not only drastically changes the form and texture of pre-existing deposits, but it also creates a new ones. Like metamorphism happens in any orogenic terrain where deformation and metamorphism are attendant metamorphism are taking place, and due to this a lot of fluid is taken out during the progressive metamorphism, prograde metamorphism, and this fluid actually scavenges the metals from the pre-existing rock and deposits into the newly found metamorphic rock. So these newly found metamorphic minerals or the ores or the rock forming minerals under changed conditions of pressure and temperature are called metamorphogenic deposits. There is a difference between a metamorphosed and a metamorphic deposit. Like uh, metamorphosed deposits are those which are found by transformation from a pre-existing ore deposit or a rock forming mineral deposit. But metamorphic deposits are those which form due to the activity of water or carbon dioxide, which are released in plenty during prograde metamorphism, and they actually scavenge the metals from the rock types in which this metamorphism is taking place and deposit into the same unit along bedding planes or the foliation planes or any weak structural planes like shear zones or fault zones, etc. Means existing minerals will form metamorphosed deposits, whereas metamorphic deposits will form because of the scavenging of metals due to the activity of water and carbon dioxide during the deformation and orogenic activities. Deformation and orogeny leading to fold belt development or crustal reworkings in cratonic areas are the main causes of this metamorphic deposit formation, and different stages of the fold belt evolution from Precambrian to Proterozoic times are crossed by numerous regional deformation zones. So these deformation zones are longitudinal mostly, are of tens or hundreds of kilometers long and centimeters to kilometers wide, half kilometer to 1 kilometer wide, ductile, mostly ductile shear zones or brittle ductile shear zones. One such example is the Ghatol shear zone in the Bhukia gold prospect of Rajasthan. There are several such shear zones like Delwara shear zones, the Rakabdev shear zones, the Fulad lineament, which is in Fulad shear zone, the Banas dislocation zone east-west trending, which actually separates the tectonic terrain of the area, the basement niches of this Rajasthan craton from the Aravalli fold belt. So these are the tectonic domains which create tectonic amalgamation of these tectonic domains actually create a uh, lot of mineral deposits along these major shear zones or within the rock types which are present within the tectonic zones. During this deformation and attendant metamorphism, obviously the minerals will be stressed because of compression, either pure or simple shear, and extension, and obviously a cystosity or nisosity or a flow structure will be created into the rock type, into the minerals, individual minerals, and they will be reflected in the rock type. So galena, for example, becomes gneissic or even rendered so fine grained that individual cleavage surfaces cannot be discerned with it around it, and hard minerals such as pyrite and other minerals like chalcopyrite, bornite, covalite, stibnite behave in a similar way. The hard minerals behave in a different way, and the softer minerals like this chalcopyrite, bornite, etc., they will behave in a different way. Like during metamorphism from chalcopyrite, this bornite and this covalite, this cubanite, mostly cubanite is exolved at higher pressure and temperature conditions from chalcopyrite. So they are the metamorphic deposits. They are the deposits formed due to the change in the mineral composition of the pre-existing mineral because of the rise in the pressure and temperature condition and the activity of mostly water, H2O or CO2 as the case may be. So the result is that the ores exhibit streaked, banded, smeared appearances with indistinct boundaries between minerals of different color. That means this ore will be, as I have said, because of the flowage, they will be streaked, they will be banded in nature because of the cystosity developed or the nisosity developed. They will be smeared in the rock type throughout the foliation with indistinct boundaries. The boundaries will not be very distinct of the different minerals. So the original texture and the structure is in this way obliterated, and the original deposits changed totally. That is, the pre-existing ores are metamorphosed ores formed. The pre-existing ores changed to a metamorphosed ore body. So metamorphic ore bodies form, on the other hand, metamorphosed and metamorphic. There is a difference between these two. Metamorphosed, I have already told. Metamorphic is the one which actually comes from the is the mineral formed due to the scavenging of the metal from the rock itself due to the excessive fluid generated during metamorphism. And so metamorphic ore bodies, on the other hand, form due to adjustment between the chemical potential of any system and the changes in the temperature and pressure during metamorphic process as a result of deformation and orogeny. That means during the orogeny, fluid generated in a high quantity that actually scavenges the metals and deposits into the rock type itself. And in this examples are of gold and copper deposition is very much so. We must look after gold and copper deposition or metamorphic bodies into the fold belt terranes very skeptically and along the mostly along the major shear zones or within the fold closures and limbs, etc. One reaction which does not take place at a lower temperature will certainly, like reaction between pyroxene and plagioclase, may not take place at a lower temperature, but at a changed temperature and pressure condition, at a higher temperature pressure condition, it will change to garnet and other minerals. An increase in the temperature normally results in endothermic reactions. A possible example is the conversion of pyroxene to hornblende during metamorphism of a dolerite or a diabase, or dolerite or gabbro or diabase to amphibolite, where an endothermic reaction changes the pyroxene to amphibole plus your plagioclase. In a fold belt evolution or in an orogenic terrain, so progressive deformation in that terrain will increase the pressure temperature conditions, and obviously an attendant metamorphism will take place where the mineral readjustments will take place. Along with the intricate folds formation, there will be a formation of ductile shears mostly because the temperature is higher, and these intense ductile shears and structural disturbances will lead to formation of certain deposits in that terrain, in that fold belt. Shear zones may be from centimeter to meter to kilometer scale, paralleling the axis or the axial planes or the limb of the major folds. But I have already said that within two major shear zones, tectonic domains are this way found during the deformation and metamorphism of intense nature, and independently developed tectonic domains or terranes. Certain terranes are developed bound by two shear zones in which a unique combination of rock types will be there, and the combination of structural and metamorphic histories will be created individually. These shear zones are in later phase amalgamated during later deformations also, and they come together and stay, or they are seen at present side by side. Like here in the cratonic terrain, we have identified in Rajasthan several tectonic domains of individual group of rock types which share their boundaries with the next tectonic domain, which contain a altogether different combination of rock types with their, but the deformation history almost remaining the same, or they are similar in nature. So these shear zones and the which shear zones which are acting on the host rocks, they are basically, the shear zones are basically the pathways for the generation of liquids, and the liquids goes through these shear zones and containing the mineralizing fluid and deposits them into the rock types present inside the tectonic domain. So at a later stage, when the brittle nature starts after the ductile shearing, so late faults and veins and conjugate type of veins are developed, and which also impregnate the host rock with the mineralizing fluids which are generated during the earlier stage of metamorphism at a higher PT condition. So we get a continuous process of mineralizing fluids being deposited during ductile deformation and followed by brittle deformation in any metamorphic terrain, or any terrain undergoing deformation and metamorphism, or any terrain undergoing a orogenic evolution. Recrystallization of ores in the early stages may be overprinted by cataclysmic formation of breccias with the new ore mineral precipitation throughout the host rock. The pervasive deformation at a regional scale will certainly make certain high strain zones at relatively lower temperature and pressures, and these high strain zones are very important for search of mineral deposits in any fold belt terrain. Shear zones are very important. Within the major shear zones, there will be micro shears, several micro shears in different directions of different generations, and mineral along the mineral grain boundaries also. These are the fluid of the mineralizing fluid that penetrates through it and deposits its metal into the host rock, resulting in local scale alteration and replacement in the host rock, such as local development of quartz veins, amphibole calcite veins, amphibole veins, biotite, epidote, magnetite, ilmenite veins, and aggregates, etc. So these shear zones are very important, brittle and ductile both, in terms of their mineralizing solution being deposited into it and into the rock type. So this fluid flow is not generally controlled by open fractures, cannot, because these will have to be closed fractures like brittle shear zones or ductile shear zones. If they are open, the fluid will not flow. If they are not open, they are pervasive into this terrain, into the fold belt terrain. So this fluid flow will take place along the foliation planes, along the micro shears, along the grain boundaries, etc. of the rock type, and they deposit in a certain conducive place where they are mostly accepted by the lithological conditions and the petrological conditions. After uplift into the brittle regime, once from a depth it comes up, the unit comes up, the rock type comes up during fold belt evolution into the brittle regime. The fold belt may also undergo tectonic extension. Extension will follow compression, obviously, and it will be accompanied by steeply dipping veins with the mineralized normal faults, etc. So normal faults will develop into these fold belt terranes, and this will be containing the mineralized fluids which have been generated during the progressive ductile deformation. As I have already told, that metamorphism dehydrates the rock types and lot of water is generated. These H2O, or in case of carbonate rocks, the CO2 activity of CO2 scavenges the metal from the rock types and it deposits uh, into the place where this metamorphism is taking place, means the rock type itself, which is being changed gradually. So metamorphic dehydration fluids beneath the modern collisional origin have leached most of the arsenic, and this is the case in our Bhukia also. Possibly these metals were already present. This presence of metal is because of the dehydration fluids beneath the collisional origin behind below the Aravali fold belt. In this case, specifically in the Bhukia case, that gold is leached from the amphibolite facies rocks, and it is transported into these elements to shallower levels, resulting in crystal scale metal mobility from deeper parts of the metamorphic pile. So, in any fold belt development or orogenic evolution of the fold belt, the metamorphic fluids scavenge the metals they deposit within the rock type and are taken up during the upheaval or during the whole process, making the deposit coming out to the surface of the earth during our fold belt evolution itself, and because of the uplift of the terrain along the major ductile shear zones. Hence, all late metamorphic deformation zones should be considered conducive for base metal accumulation and gold accumulation. So these metamorphic deformation zones are very important, and they are essential places to search for gold and base metal accumulation in any metamorphosed or any metamorphic deposit. Some of the examples are here. The Witwatersrand gold uranium ores and the Zambian copper belt ores have suffered greenschist facies metamorphism, and the Lake Superior iron formations have suffered amphibolite facies metamorphism. The degree of metamorphic alteration depends not only on the metamorphic grade, but also on the original composition of the ore. So susceptible deposits can show the effect of both prograde and retrograde metamorphism, and therefore their original paragenesis or the mineralogy is extensively modified, if not at all destroyed. Therefore, great care should be taken in interpreting the results by using geothermometers and geobarometers obtained from metamorphosed deposit. So, since this metamorphism, prograde and retrograde metamorphism change the original paragenesis, the PT condition of the deposit identified through the later developed minerals should be very carefully taken, and the readings should be done in such a way that the original temperature pressure condition of the host rock comes in. So new minerals or the new mineral assemblages are a common result of metamorphism of iron and manganese deposits. The silicate minerals in these deposits, iron and manganese, are formed at the expense of the primary oxide, hydroxide, or carbonate minerals. In sulphide assemblages, of course, the new changes include pyrite altering to pyrrhotite, tetrahedrite tennantite altering to arsenopyrite, chalcopyrite, sphalerite, and bathyerite, and the formation of spinel, magnetite, and garnite, etc. However, the most striking feature of metamorphic alterations are their changes in texture and fabric. Here also we can say that one good example is the formation of cubanite from chalcopyrite. At a higher PT condition, these blades of cubanite are exalted from chalcopyrite, taking the metal from chalcopyrite itself, and a new mineral assemblage is formed. This is how the metamorphism alters the pre-existing mineralogy, and a new deposit is found in this way. So refractory minerals, which are like pyrite, arsenopyrite, sphalerite, magnetite, etc., they show little change with the low-grade metamorphism and retain their primary compositions. But with higher grade of metamorphism, they change. With greater metamorphism, they lose their zoning our say arsenopyrite change to lowlingite, and these sort of things happen at a higher temperature and compositionally re-equilibrate and retain this composition through retrograde metamorphism. The case of arsenopyrite is that at lower temperature, in a brittle deformation, they actually crack and make a granular appearance. But at higher temperature, the arsenopyrite changes to lowlingite, and finally, because of the more higher temperature and pressure conditions and the presence of suitable composition, some base metal or gold is incorporated into the structure of mostly in lolingite, the gold is incorporated. Similarly, in chalcopyrite, we have some other higher grade minerals of the copper ores. Therefore, these metamorphism have limited value in determining the initial formation conditions. They deform by twinning. These minerals that deform by twinning and the kink banding, but primarily they flow. These minerals which I have been citing just now. This leads to the mechanical breakup of the ore and country rock and produces very diagnostic Bewegung structure or ball textures and the presence of injected sulphides along cleavages and fractures within the harder ore and gangue phases. So chemical etching of sulphide ores is helpful in determining the change in the fabrics with metamorphism. This is especially true for massive ores containing the isotopic minerals like pyrite, galena, and sphalerite. In essence, I would like to say that metamorphism changes the ore body of a pre-existing type. Say, for example, if an ore body of igneous origin or sedimentary origin that changes because of metamorphism and because of deformation and attendant metamorphism. But metamorphic deposits will certainly form due to metamorphism, due to the fluid released during prograde metamorphism, and this fluid in time leaching out the metals from the rock types itself and depositing into the present rock types uh, along the major shear zones, micro shear zones, fold zones of brittle nature, and fold hinges and fold axial plane along the axial plane of folds, belts, etc. Thank you very much.
Thank you, sir, for such a fascinating lecture. Can you please give a brief of how do you think metamorphic petrology can be used in mineral exploration?
This is my with my experience I am telling in this Rajasthan terrain. Say for example, Mundiawas Khera area. This is a gold, basically a copper deposit with some quite good amount of gold and silver. Here we can see normally what happens, say in carbonate rocks. Normally it's a, say it is a dolomite or a limestone. Say it is a dolomite having no grains of visible grains of tremolite, actinolite, etc. If you in the field suddenly get concentration of lot of tremolite and actinolite, such minerals, or even wollastonite, so your eyes should be very skeptic in looking into it, and your ears should be very open to see that, listen to the history. Like that, suddenly these minerals cannot develop unless there is a change in pt condition. And if there is a change in pt condition, as I have told you, fluid action or the CO2 action, activity of CO2, in this case specifically in the carbonate rocks, the activity of CO2, that actually crystallizes these minerals in a plenty in one place, and that indicates on the surface that suddenly this thing has come because of normal paragenetic sequence. This should not happen. It is something abnormal in the field. So these are the zones where you suddenly get within the dolomite a concentration of tremolite, actinolite, or wollastonite. So these are the zones which will reflect that some mineralization has taken place, and they could be termed as ore zones or mineralized zones or alteration zones, or they may be termed in later cases after you find it. This has been tested in this area. In Bhukia area also similarly it is tested. You find that these are actually the mineralized zones, and the deposit, if you make a borehole into it, you get a deposit, a load or a zone of sulfide and gold mineralization. So this is one example I have given where you suddenly get a change in the mineralogy in the hand specimen itself. Suddenly you get a concentration in bands or lenses of this tremolite, actinolite, or wollastonite in a carbonate rock. So you have to be very inquisitive, and you have to look into these sort of things. Similarly, in the, say it is a schistose rock, if you get suddenly certain minerals which are not being seen physically by hand lens or so into in the field. Say for example, you say see suddenly the strawlite and garnet are getting suddenly at one place. So bulk composition plays a role in formation of these minerals. But at the same time, if the normal metamorphism which has happened into that whole package, in certain parts abnormally high when proportion of these minerals cannot happen unless there is some mineralization. This is what I think, sir. And similarly, in the basic rocks also, if you go into the amphibolites, suddenly you will find some of the places coarsening of the grains of the amphibole, or if the pyroxene is present at all in that place. So these are the features which should be looked into the field while going for exploration of any metamorphic deposit. And what I have seen in Rajasthan, most of the deposits are either metamorphosed or metamorphic. You are working over a terrain of metamorphosed terrain. How can you expect a mineralogy other than the metamorphic mineralogy? This sounds very illogical otherwise. If I am working on a high grade terrain, amphibolite facies are even higher grade, maybe granulite grade terrain, and I am telling that this is a only a hydrothermal deposit or only a sedimentary deposit. So both things do not go together. You have to look into these terms that with deformation, certainly orogeny has taken place, fold belt has developed, or a cratonic terrain where the reworking has happened because of deformation, and therefore there is a mineralization, metamorphism, and formation of certain ichors also. So granite fluid is found in tectonic terrain, granitic fluid or similar fluids are found depending upon the host rock. These alterations will certainly scavenge certain metals and they will deposit. So these zones of shear zones and unusual mineral zones, normally say what I said just now, you get garnet and stolite extraordinarily in certain parts. So you should look into that area. Say tremolite, actinolite or lustenite in certain parts in the carbonate, you should look into that area. This is how one should proceed in a metamorphic terrain or any terrain of high grade or medium grade area.
This what you are saying is also re-establishing the importance of proper detailed mapping in any kind of exploration work. Uh,
Exactly.
and what you are suggesting is probably also that metamorphic characterization and study of pressure, temperature, PT conditions of metamorphism may be used as a vectoring to find the locations of minerals, mineralization, and probably also to the grade variations within the mineralized body.
Itself. Yes, you are very right. Even if you don't go for PT condition estimation, the physical presence of these minerals, the paragenetic sequence, you can simply make out from the thin sections or the ore sections. And this paragenetic sequence, and as you have seen in the field, you have to map very carefully this metamorphic terrain, highlighting the zones of this unusual mineral development in any terrain. So these will clearly give a picture of the ore bodies, suspected ore bodies. I am not calling that there will be certainly ore bodies, but there is a suspicion, and it is found by me in my case of field mapping. In specifically, I am talking about the Bhukia Gold Project. I had identified these zones in my map, and I gave boreholes. Identify these zones as the mineralized zones, and I got the success. Whereas my colleagues who did not accept these ideas, they went for random drill hole locations away from these areas and they just failed. So finally, in certain blocks, which I have done 2 or 3 blocks, my method of approach in the field mapping, specifically during the detail mapping 1:1000 or 2000 scales, these zones should be very carefully demarcated. Nowadays they are done, my days it was theodolite, now it is by GPS survey they do it, so it is more accurate. So these are the zones should be demarcated on the DM, so that you give boreholes and you plan your way of action for exploring the deposit. And I am sure these are the only way out. There is nothing you can yourself make out. The logically, how suddenly one mineral can come out in plenty at one place and get accumulated in one place. There are no veins, there are nothing. It are not vein deposits and the rock types. Certain places you are finding that these things are not present. Say carbonate, what I gave an example. You do not get the concentration of tremolite, actinolite, or austenite. But at certain places you get it. So those certain places where you get this concentration, you have to just make a rough boundary of that area through your mapping, and these will be serving as the ore bodies, and you can identify them as ore bodies in a metamorphic terrain. sir.
Again, you are reconfirming the importance of very detailed mapping. Sometimes what happens, many geologists go into out in the field and they observe something which they don't understand.
Hmm.
There is often a tendency to ignore that observation, whereas that can be the most relevant observation they are actually
Yes.
making.
Yes, yes, that is true. And these are very small observations. I think any geologist who has studied up to MSc level, he should have acumen to see logically anything, that why I am getting this thing in plenty, or this is variation from the earlier place I have seen. So in the map, everything thing should be at least located. Even if you are not in a position to interpret it at that moment of time, you can discuss it with your colleagues and others and ask that why this is a difference. Somebody will certainly tell you the reason behind it. Your actual faithful noting of the data from the field is very, very important, and that is why you can you know it very well that nowadays there is a tendency of going for chemical analysis and everything, and giving the genesis and every model on that basis, without going into the details of the field character, which is very much important. Geology cannot be done without field detailing. Field detailing, and it is afterwards the chemical analysis and other scientific laboratory works will only substantiate the field data you have generated. So this field characterization is very much important. You have to go on foot on every each inch and foot of that area, and that then only you can identify the genesis or the how this deposit has formed, how it is making a deposit, making certain loads, or some detailing obviously comes afterwards. So initial mapping has to be very, very important thing, and every aspect has to be taken into consideration while mapping the area by anybody, any MSc student. They should go and see the things and faithfully observe, and they should not be ashamed of that. My teacher will say that, okay, you have done something wrong. They should not be ashamed of that. Okay, if he says so, it is wrong. Okay, fine. With some logic, if the teacher says it is wrong, fine. But you have noted certain things which were unusual to you, you could not make out, but at least you have noted the thing. That may be right or wrong.
Thank you, sir, for such a wonderful presentation and highlighting the again re-highlighting the importance of having a very faithful observation and recording of that thing. Many of these things, like you have already said, have led to a discovery of gold deposits in Rajasthan, which were worked by you. Thank you so much for such a wonderful presentation.
Thank you very much, sir.
Thank you for watching the video. I invite you all to please visit the Mineral Exploration Academy website and register yourself. The registration is free and registration is open to students, teachers, professionals, or anybody who is interested in mineral exploration. The registration will also provide you an access to be able to ask questions from our experts and also provide an opportunity for established experts to answer and interact with the students. The registration form is available on the Mineral Exploration Academy website. I would also encourage you to look at the editorials and opinion sections and visit the student question and answer section at the bottom here. In the student question and answer section, the questions asked by the students are being answered by our experts. Our experts are the top people in the field, and it would be a wonderful learning opportunity for the students for probably the questions that occurred to you but you could not ask, or to review questions what have occurred to other people and get the answers the different experts are providing. Thank you so much, and I look forward to interacting with you a lot more.